In 9.2, what we're going to do is we're going to look at the properties of what we call a unit circle and the functions that we can create from the unit circle. So first of all, when we talk about a unit circle, that would be in this first picture, we have this circle, and this circle has the property that the equation is x squared plus y squared equal to 1. The center is going to be at the origin, or the point 0, 0, and the radius is going to be 1. I'm going to define some functions based on our unit circle. Let's just take any point on our circle and we'll call that point xy. Notice that if I draw a ray, and let's see if I can actually draw a straight line coming out, close enough. Then what I've done is I've created this angle where the initial side is our positive x-axis. So this is similar to what we did in our prior section. And the terminal side passes through this point xy. We're going to have some angle theta that we create from these rays with its vertex at 0, 0. So what I'm going to do now is that point x and that point y, what I'm going to do is I'm going to create two functions where I'm going to call the cosine function, which we'll abbreviate as COS. With respect to this angle theta, I'm going to let that be my x value. And I'm going to let the sine function, which I will abbreviate SIN, of that angle theta, that's going to be the y value with respect to this point x and y on my unit circle. So I can replace the point xy with the notation cosine theta, comma, sine theta. And these are our first two what we call trigonometric or trig functions. In this particular textbook, they're calling it circular functions because they're from the unit circle. So whether you say trig or circular function, it's going to mean the same thing. So now let's look at this point 1, 0. So at this point 1, 0, for example, that would be where theta, the angle measurement is 0, right? So we have a theta angle of 0. So at this point, we would write cosine of 0, because that's our theta value, is equal to the x value of 1. And sine of the angle 0 is equal to 0. So we could do that with any point on this unit circle. And the reason why we want to create these functions is because circles are what we call perfect. They're perfect in that they have all the symmetries. Notice if I was to reflect about the x-axis or the y-axis, the shape of the circle doesn't change. It stays the same. If I do a rotation, either left or right, the shape of this circle remains the same. And if we talk about going along a circular path, we can go forever and ever and ever in either direction, either counterclockwise or clockwise, and never stop. So it has this property of being infinite. The problem with circles is that they're not functions. So the reason why we're creating these circular or trig functions is so that we can create functions that have some of the properties of a circle, because they're super nice, but they're actually functions. So why do we need functions? Well, in the real world, what you want to work with is a function. If you put in some value, x, into a function, you better get back one value, y. For example, if I were a doctor and I was going to figure out the dosage for a patient, I would put in their statistics, height, weight, and so on. And I better get one dosage back from my function. If I get more than one choice, I may be prescribing the wrong dosage to a patient and they could die. So in the real world, we want to work with functions. Circles are not functions. However, because they have all these great properties, we want to create functions from the circle. And we want to create functions that perhaps can go on infinitely in both directions, what we call periodic functions. And this is where our cosine and sine come from. So cosine is the x value on the unit circle. Sine is going to be the y value on the unit circle. So our goal is to first look at any angle theta and describe our trigonometric or circular functions. And then later on, we're going to move away from the circle and we're going to take these trig functions and we're going to apply it to right triangles. So our goal is to get to right triangles given any angle theta, we can use these trig functions. So if we look at this next diagram, again, we have a unit circle. So for example, let's look at, and we'll review some of the trigonometric functions from geometry. Let's look at this point that we have on our circle. So this point is a point square root 2 over 2, comma, square root 2 over 2. At that point, and again, we're on the unit circle because notice the radius here is 1. So that distance is 1. If I were to drop a vertical line from the point to the x-axis, what I've done is I've created this right triangle. And in this particular case, the angle theta that corresponds to this right triangle is a 45-degree angle. So remember from katoa, our sine function is going to give us the opposite over hypotenuse. So the sine of theta, in this case it's 45 degrees, is going to be equal to the opposite side from the angle, which would be the square root 2 over 2, over the hypotenuse. In our case, our hypotenuse is just 1. So sine of 45 degrees, which is square root 2 over 2 over 1, in the case of the unit circle, would just simplify to the square root 2 over 2. So you could check that in a calculator, put in sine of 45 degrees, make sure you're in degrees, and you'll see that you'll get approximately 0.7, which is the approximate value of square root 2 over 2. So again, this is the goal. This is where we want to get to. We want to get to given any angle theta, and we're going to move beyond the unit circle. We can use the properties of the right triangles along with these trig functions to solve a lot of different problems. Notice that at this particular point, it's still the cosine of 45 degrees. That we still have square root 2 over 2 because cosine would be the opposite, or the adjacent, sorry, over the hypotenuse. You get the same value. So in a 45-degree angle right triangle, the sine and cosine values are going to be the same with respect to our angle theta. Now when we're dealing with angles, it really doesn't matter what the radius of our circle is, which is why we can apply these trig functions to any hypotenuse, because when you think about it, and I'm going to try to sketch a circle, although it might not turn out well. If you think about it, if we were looking at a smaller circle, let's say the radius was a half, and I'm going to try to draw this as half. So notice that the point I chose, the square root 2 over 2, square root 2 over 2, that was the halfway point in the first quadrant of that unit circle. If I decrease the radius and I look at where the ray intersects this smaller circle, it's still the halfway point with respect to this smaller circle in the first quadrant, but notice the angle did not change. I could also pick a larger circle, and extend this ray, it's going to, on the larger circle, it's going to intersect at the point that is halfway in the first quadrant. Angle is still 45 degrees. So the point of this is to show you that it really doesn't matter the radius of the circle I choose, the angle is going to stay the same, which is why eventually when we take these right triangles and we take them away from the circle, the hypotenuse can be any length, but the sine, cosine, tangent functions, they're going to remain the same with respect to that angle theta. So again, that's our goal, to get to the right triangles using our trig functions. But first we're going to start at the beginning, and we're going to look at, instead of an angle theta, we're going to look at an arc length. Again, we're still talking about the unit circle here. So in this diagram, notice that given any point x and y, and here we're in quadrant 2 for our example point x and y, it's going to correspond to an arc length, and it's going to correspond to some angle theta. So in this case, we have our arc length. So remember, our arc length was s, and then it also corresponds to some angle theta. In the case where you're looking at the unit circle, which is what we're looking for, the arc length and theta are going to have the same measurements. So remember the formula for arc length. S is radius times angle theta in radians, right? But here, since the radius is 1, our arc length and our angle theta are the same. So we're going to start out with arc length as opposed to angles, which is going to be our eventual goal, because it's easier to describe distances in terms of an arc length. Remember, our angle theta is more like a rotation, where the arc length is a distance or a length. So that's easier to work with. So again, here our cosine of theta is going to be equal to cosine of, now we're going to use arc length S within the unit circle. And sine of theta is equal to sine of our arc length S. In this example, we could see the cosine of the arc length is equal to the x, sine of arc length is equal to y. This relationship only works, the relationship between arc length and angle only works if we're restricted to the unit circle, because in this case, arc length and theta have the same value. Again, remember, our goal is to get away from arc length, go to angles so that we can create any radius or any hypotenuse and still use all of our trig functions. But for now, we're going to remain in arc length because the length is easier to vision rather than angles. So we have what we call our circular or trigonometric functions. And we already talked about sine being our y value and cosine being our x value. We're also going to define our tangent function, and that's going to be the y over x. Since x is in the denominator, x cannot be equal to 0. We're going to define another trig function, which is cosecant. Cosecant is the reciprocal of the sine function. So if sine is y, and you flip it, so it's y over 1, and you flip it, you get 1 over y. So if you flip sine, you get cosecant. So here the y can't be equal to 0 because it's in the denominator. Now if we look at cosine of x, or cosine of x over 1, and you flip it, you get 1 over x, and then that would be our secant function. It's 1 over x. Cosine, flip it, you get secant. X cannot be equal to 0. And then the last trig function we're going to talk about is cotangent. So cotangent would be the reciprocal of tangent. So notice the tangent, if you flip it, you get x over y. So in this case, the y value cannot be equal to 0. So let me write out our functions in long form. When I say the sine function, it's just written as, oops, I don't want that. it's written as SIN as an abbreviation, but the full name is sine, SINE. Cosine is COSINE. Tangent, TANGENT. I can't even spell. And then we have our cosecant, the CSC. So that's going to be COSECANT. So that would be our cosecant. SEC stands for secant. And then the last one would be COT, which is cotangent. And then these would be our 6 trig functions. The 3 main would be sine, cosine, tangent. And then when you take the reciprocal, you get the other 3, which is more secondary functions that we don't use as much. And that would be the cosecant, the secant, and the cotangent. One thing that's going to come up a lot in our trig functions is notation. So going back to our unit circle, notice that if we have any point x and y on our unit circle, we can replace x with cosine of the arc length s, y with sine of our arc length s, so cosine s, sine s, and those would be our points x and y. Going back to our equation, x squared plus y squared is equal to 1. Since x is cosine of s, we can replace x with cosine s and then y with sine of s. So in that equation, x squared plus y squared equal to 1, we can write it as cosine squared of s plus sine squared of s equal to 1. Now, notice that the square is after the name of the function, but before the argument, which is just the value we're putting into the function. In this case, it's our arc length s. So in any of these trig functions, if you see an exponent between the name and the argument, that means that you are, in this case, squaring the whole function. So another way to write this would be if we take the cosine of s and we square this whole thing, and sine of s and square the whole thing. These mean the exact same thing. You have to have the parentheses there. And since we get lazy, again, mathematicians are lazy, that's why we create symbols so we don't have to write a bunch of words. And you get lazy and you don't want to keep writing those parentheses, then you would have to put the exponent in between the function and the argument as we see above. So again, these are saying the exact same thing. In this box that we have here, just careful with notation. Because notice that cosine squared of s is the same as saying, well, we're going to take cosine of s, that whole quantity, and then we're going to square it. However, if you write cosine squared s, it's not equal to cosine of s squared. Those are very different. And if you were to put both sides into, say, Desmos, y equal to cosine squared s and y equal to cosine of s squared into a graphing calculator or something like Desmos, you'll see you'll get very different graphs. And that's because cosine of s squared without the parentheses is saying cosine of the quantity s squared. So in this case, the square only applies to the s, not the whole function. So just be careful because it's quite efficient and more common for us to put exponents between the name of the function and the argument. So let's move on. Since we are talking about functions, it's going to be important that we talk about domains. First, note that when we look at our x values, and here again, we're just looking at the unit circle. So you can see the unit circle down below. When we look at our x values, they go from -1 to +1. inclusive, so it can include -1, +1. So remember, x is our cosine value. That means cosine, put in an arc length s, you can only get values from -1 through +1. Similarly, our y values, -1 to +1. Substitute sine for y, and you get the sine values go from -1 to +1. So remember that in a function, you put in some value, in this case it's our arc length, what you get back, these -1 to +1 values, that would be the range. So in this case, this would be range of our cosine function and the range of our sine function. Now let's talk about domain. And we'll look at the domain for all 6 functions. When we look at sine and cosine, it's really nice. Sine and cosine, we can put in any arc length. So we can put in any value for sine and cosine. What we're going to get back, our range, is going to be -1 to +1. But we could put anything in for an arc length, because remember, the arc length is a length along the circle, and we can go along the circle as many times as we choose. We can start and go in the positive direction or counterclockwise. We can go a length of 2 pi, but we can keep going around again and again and again and again, forever and ever, which means we can actually put in any value for arc length. And we can put in negative values as well if we went in the opposite direction. Again, but the range, the only thing that comes back out are values from -1 to +1. So let's look at just the domains of the remaining 4 trig functions. We'll talk about range at a different time. And it's going to be a little weird when we define them. Let's look at tangent and secant, because they're going to have the same domain. And this domain is written in set builder notation, going back to Math 135 when we talked about set builder notation. So remember, we're putting in the arc length S. So this says the domain is going to be all arc lengths except for an arc length so the arc length cannot be equal to 2n plus 1 times pi over 2. And here the n that we're talking about is any integer. So before we talk about the domain for cotangent and cosecant, let's talk about why it's written this way. And it's written this way because it's an efficient way to write the domain. Okay, so let's think about this. Remember that tangent and secant, remember that they had x in the denominator. So tangent was y over x, secant was 1 over x. So our x value could not be equal to 0. When we look along at our unit circle and we look at where our x values are equal to 0, that would be at pi over 2, the x value is 0, and at 3 pi over 2, the x value is 0. But remember, we can go in positive or negative direction forever. So when we actually think about this, cannot be equal to pi over 2. It cannot be equal to 3 pi over 2. But if I was to continue on and keep going around the circle, so we're at 3 pi over 2. If I go back and continue on, then this is going to be 5 pi over 2. So pi over 2 is the same as saying 5 pi over 2. And if we continue on, another distance of pi will be at 7 pi over 2, and so on. So we can keep going around. Well, what if we went in the other direction? What if we start at 0 and we go to negative pi over 2? Well, at negative pi over 2, the x value is 0, so we have to take that away. Now let's continue on. Negative pi, this is negative 3 pi over 2. At negative 3 pi over 2, the x value is 0, so we can't use that either. So notice that we can keep doing this forever in both directions, both the positive and negative directions. So it's very difficult to list all the values that we cannot use in our domain for tangent and secant. So the most efficient way is to look for a pattern. If you look at these values, the negative 3 pi over 2, negative 1 pi over 2, 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. It's just odd numbers, negative 3, negative 1, 1, 3, 5, 7, and so on. So one way that we can write odd numbers is by this 2n plus 1. So think about this. If n is 0, because n is any integer, if n is 0, then this is 1 times pi over 2, which would give us that positive pi over 2. If n is 1, then it's 2 times 1, which is 2, plus 1 is 3. 3 times pi over 2 gives us 3 pi over 2. If n is 2, then it becomes 5 times pi over 2, which gives us the 5 pi over 2, and so on. If we go in the other direction, remember n is an integer, so it could be negative numbers as well. What if n is negative 1? Then 2n plus 1 becomes negative 1. So it's negative 2 plus positive 1 gives us negative 1 pi over 2. If n is negative 2, then it becomes negative 3 times pi over 2, or negative 3 pi over 2. So this set builder notation, which you don't have to memorize, is an efficient way for us to describe the domain of tangent and secant. When we look at the domain of cotangent and cosecant, based on what we just looked at for tangent and secant, it'll become easier to understand this set builder notation, which is the set of all arc length s, such that s is not equal to n, so remember n is just an integer, times pi. So let's go back and remember that cotangent is x over y, cosecant is 1 over y. So we have to take out any values, any arc length that corresponds to a y value of 0. Going back to our unit circle, looking at where y values are equal to 0, that would be here at our initial point 1, 0, and at negative 1, 0. If we look at this circle and we start at 0 and we travel around, we've gone a distance of pi, and that y value is 0. If we keep traveling and go another distance of pi, we're back at where a y value is 0. So all these distances of pi, all these multiples of pi, correspond to points where the y value is 0. For example, if we're at 0, we can't use that, and this is the arc length of 0. If we're at an arc length of pi, can't use that because the y value is 0. And then 2 pi, if I go around another pi, I'm at 3 pi. We can't use these values, but we also can't use negative pi. If we were to go in the opposite direction, starting at the point 1, 0, and go opposite a distance of pi, we will get to the point where the y value is 0, so we can't use negative pi. Keep going around, we'll be at negative 2 pi, and so on. So we have to take these values out. The most efficient way to write that is by n pi. So take any integer times pi, and that will correspond to one of these points. If n is 0, we're at 0. If n is 1, we're at pi. If n is 2, we're at 2 pi, and so on. Going the other way, if n is negative 1, we're at negative pi. Negative 2 is negative 2 pi. Again, you don't have to memorize set builder notation for these domains, but you should know that at multiples of pi, cotangent, cosecant are going to be undefined. And at multiples of pi over 2, odd multiples of pi over 2, tangent and secant are going to be undefined. So initially we had defined these trig functions, the 6 trig functions, in terms of the point x and y. But we can also replace the x with cosine and the y with sine, which brings us to some properties that you will naturally memorize most of these because we'll use them so often. And the first ones are going to be what we call the reciprocal identities. All we've done is, remember, tangent was y over x. So all we did was replace y with sine, x with cosine. So another way to find tangent values is by looking at sine over cosine. If we were to take the reciprocal of tangent, we get cotangent, which means we're just going to flip sine and cosine. So cotangent is cosine over sine. So remember, secant was 1 over x. Replace x with cosine. And cosecant was 1 over y. We replace y with sine. The other identity we're going to look at is, we already talked about this earlier when we looked at the unit circle x squared plus y squared is equal to 1, and then we replace our x with cosine, we got cosine squared. And then the y with sine plus sine squared is equal to 1. So this is a Pythagorean identity, cosine squared plus sine squared equal to 1. That's going to be ingrained in your brain. You will remember that. You may not remember these other two, but it's not necessary, because you can always start with cosine plus sine, cosine squared plus sine squared equal to 1, and get these other two Pythagorean identities. So let's say we want to get rid of cosine squared. What I can do, this is an equation, is I can divide all the terms by cosine squared. So cosine squared over cosine squared is just going to be 1. But what I do to one term, I have to do to all terms in an equation. The cosine squared over cosine squared is going to give me the 1 in this next identity. Sine over cosine is tangent, so sine squared over cosine squared is going to be the tangent squared. So we get 1 plus tangent squared. And then 1 over cosine is secant, so 1 over cosine squared is secant squared. So you actually don't have to memorize the last two identities. As long as you have the first one, you get the others. Well, let's just say I wanted to write the Pythagorean identity in terms of, instead of tangent and secant, maybe cotangent and cosecant. Go back to cosine squared plus sine squared equal to 1. And this time we want to get rid of sine. So we're going to go ahead and divide everything by sine squared. Cosine over sine is cotangent, so cosine squared over sine squared is going to be cotangent squared. Sine squared over sine squared reduces to 1. And 1 over sine is cosecant, so 1 over cosine, or 1 over sine squared is cosecant squared. Now let's look at some examples where we're using this idea of arc length and our trig functions. And I worded example 1 so that it kind of corresponds to the language that you would see in our textbook. In example 1, it says for each number s, so for each arc length, determine the point on the unit circle to which it corresponds, and then determine cosine of s and sine of s. State which functions are undefined for s. Looking at A, remember this corresponds to an arc length. So this 0 is your S value. So for an S value of 0, what you would do is you would go back to the prior diagram where we had the unit circle with the points 1, 0 for 0. When we go in an arc length of pi over 2, we're at the point 0, 1, and so on. So if you look at that unit circle and you look at where we have an arc length of 0, that would correspond to the point 1, 0. So our cosine of S, in this case our S is 0, cosine is going to be the x value, of 1, can't write, and sine of 0 is going to be the y value of 0. So we found cosine of 0 and sine of 0. Now we need to state which functions are undefined for the arc length of 0. So remember, we're at the point 1, 0. The y value is 0. So any trig function that has y in the denominator will be undefined because you'll have 0 in the denominator. And that would be our cotangent and our cosecant, because cotangent is x over y, cosecant is 1 over y. So in this case, cotangent and cosecant are undefined. So you can write DNE or do UND period for undefined, however you want to write that. In part B, our S is pi. So if you go along that unit circle to pi, you'll find that that corresponds to the point -1 for x and 0 for y. Cosine of this arc length pi is going to be equal to the x value of -1. Sine of our arc length pi is equal to the y value of 0. So again, we have a y value of 0, which tells me that cotangent and cosecant are undefined. C, we have negative pi over 2. So we're going to go in the negative direction, and negative pi over 2 corresponds to the positive 3 pi over 2. That would correspond to the point 0 and -1. So our cosine of, and now when we have negative values that we're putting into our trig functions, we always use parentheses because then it would look like cosine minus pi over 2, but it's cosine of negative pi over 2. So cosine of negative pi over 2 is going to be equal to 0. Sine of negative pi over 2 is going to be equal to the y value of -1. And in this case, since it's the x value that is 0, tangent is y over x, secant is 1 over x. So those two functions would be undefined. Or you could write DNE. Okay, 3 more examples. Negative 3 pi. Again, we're going to go in the negative direction. We're going to go a distance of 3 pi. So that would be one rotation and another pi. You would actually be at the point pi. So negative 3 pi corresponds to the same point as a positive pi. They're not exactly equal, but they correspond to the same point on the unit circle, which would be -1, 0. So -1, 0, that would be like our example B, cosine of negative 3 pi. That's the same as cosine of pi, which would be -1. And sine of negative 3 pi would be that y value of 0. And sine of negative 3 pi and sine of pi, they're going to be the same. So again, since it's a y value that's 0, that would correspond to the cotangent. And cosecant, I'm just going to put in cotangent of negative 3 pi and cosecant of negative 3 pi. These are going to be undefined, or DNE does not exist. What about 7 pi over 2? Well, that's actually, if you go around one positive rotation, you end up at 2 pi, which is actually smaller than 7 pi over 2. So 7 pi over 2 means that, and let me just draw a little unit circle. It means that you're going to go pi over 2 7 times. So let's think about this. If I just go the distance in the first quadrant, I'm at pi over 2. I've gone a distance of pi over 2. Keep going around, I've gone a distance of 2 pi over 2, 3 pi over 2, 4 pi over 2, keep going, 5 pi over 2, 6 pi over 2, 7 pi over 2. So when we're at 7 pi over 2, we're at the same point as 3 pi over 2, which would be the point 0, negative 1. So that's the nice thing about the circle, is you can always count. If you're looking at pi over 2's, you just count the pi over 2's till you reach 7 pi over 2. That's one way. The other way is you can use the idea of coterminal angles, which we did in 9.1. You can just take 7 pi over 2 and subtract 2 pi until you get to a value that's on the unit circle. However, 0, negative 1, that corresponds to the same values we had in part C. The cosine of 7 pi over 2. And notice I didn't use parentheses because it's not a negative value, but you could. There is nothing wrong with always putting parentheses around the argument, because it is a function. It's like f of x, where f is cos, cosine. So cosine of 7 pi over 2 would be the x value of 0. Oops. Sine of 7 pi over 2 would be the y value of negative 1. So since the x value is 0, tangent, secant, so I'm going to write tangent of, again, you can put around the parentheses or not. And I'm going to do secant of 7 pi over 2. That these two are undefined, because this is where the x value is 0. Last one, f, we're looking at negative 7 pi over 2. So what you could do is you could keep adding 2 pi until you reach a positive value on the unit circle, or you could just look at your unit circle and you could count. This time we're going in the negative direction. We're going negative direction 1 pi over 2, 2 pi over 2, 3 pi over 2, negative 4 pi over 2. I'm going to keep going. 5, 6, negative 7 pi over 2 corresponds to the point at positive pi over 2, which is the point 0, 1. So at 0, 1, x value is 0, so cosine is going to be 0, y value is 1, sine is going to be 1, tangent and secant are going to be undefined. So we have cosine of negative 7 pi over 2 is equal to 0. Sine of negative 7 pi over 2 is equal to 1. Tangent of negative 7 pi over 2 and secant of negative 7 pi over 2. These are both undefined. Here are some little reference charts if you would like to use them. This first chart is from your textbook. What it does is it just gives you the main values on the unit circle for, here we have 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then it gives you the corresponding values for sine, cosine, tangent, cotangent, secant, and so on. So we have sine, cosine, tangent, cotangent, secant, cosecant. So if we look at 0, Sine of 0 is 0, cosine is 1, tangent is 0, cotangent undefined, secant is 1, cosecant is undefined, and so on. So you can use this chart if you would like for reference. But something else will come up, and that's the idea of when sine and cosine, tangent, cotangent, secant, cosecant, when they're positive and when they're negative based on our unit circle. So if you look at this next diagram, it represents the 4 quadrants of our circle. We're always going counterclockwise, which means in quadrant 1, this would be where x and y are both positive. So that means that all of our functions are going to have positive values. When we go to quadrant 2, so again, we're going counterclockwise, x is negative, y is positive. That means its sine and the reciprocal cosecant, because y is positive, sine and cosecant are only written in terms of y, they're going to be positive. But all the rest of the trig functions have an x in it. So they're going to be negative because it's either going to be an x, a negative x and a positive y, which would make the function negative, or it's just going to be a negative x. In quadrant 3, x and y are both negative. That means the tangent and its reciprocal cotangent are going to be the only positive trig functions if we're in quadrant 3, because you're going to have y over x, negative over negative makes positive. X over y for cotangent would be negative over negative, which makes positive. So these two are the only positive trig functions in quadrant 3. All the other trig functions are going to be negative. And then in quadrant 4, x is going to be positive, but y is negative. So functions that only have x in them are going to be positive. That would be cosine, because it's x, and that would be secant, because it's 1 over x. Those are the only positive ones. Everything else is going to be negative. So some people use this little saying so that they could remember when trig functions are positive and negative. And this is how it goes. A for all, and we're going to have S for sine and its reciprocal function cosecant. I'm going to write this as students. So all students, T would be for tangent and the reciprocal cotangent. Take. C is for cosine secant calculus. So all students take calculus is a way to remember which trig functions are positive and which are negative. So again, all in quadrant 1, sine and its reciprocal in quadrant 2, tangent and its reciprocal in quadrant 3, cosine and its reciprocal in quadrant 4. So again, these are just references, just different ways to help you to remember the values of our trig functions in the different quadrants. Let's move on to some more examples where we're using this idea of a point xy on our circle, arc length, and our trig functions, putting it all together. In example 2, we want to have S correspond to a point x and y. So S again is arc length. Go some distance, you're at a point xy on your circle. We want to find the given values for cosine and sine, and then we want to determine the quadrant where x and y is located. Okay, so for the given values of cosine and sine, we're going to determine the quadrant. This is super easy. If we look at A, sine is positive, and cosine is negative. So the quadrant in which sine is positive and cosine is negative, that would be quadrant 2. So we can write quadrant, I can't spell, quadrant 2, or oftentimes we'll just abbreviate this as Q, Roman numeral 2, or Q with a 2. So this would be quadrant 2. In part B, notice that sine is negative, but cosine is also negative. So the quadrant in which sine and cosine are both negative would be quadrant 3. So I'm just going to write Q with Roman numeral 3. Continuing on with some examples of how we can use this idea of arc length, point on a unit circle, quadrants, and so on. In example 3, we have our S that corresponds to some point xy on our unit circle. And then we want to determine the quadrant where xy is located and whether sine and cosine are positive or negative. So in this case, we're given an arc length. And we just have to determine in which quadrant we're in and whether sine and cosine are positive or negative. So if we look at an arc length of pi over 4, go back to that circle. If we go a distance of pi over 4, we're going to be in quadrant 1. So what you could do is, if you're not sure, if you put pi over 4 in a calculator, you will get approximately 0.8. So notice that in quadrant 1, we're going from a value of 0 to a value of pi over 2. And pi over 2 would be approximately 1.57, not sure, maybe 1.6. So you could see that 0.8 lies within 0 to 1.6, which means we are going to be in quadrant 1. So since we are in quadrant 1, sine and cosine, and I'll just write of S, I won't put pi over 4. They're both going to be positive. What about 2.8? Well, we know that in the first quadrant, it goes values from 0 to approximately 1.6. In the second quadrant, and perhaps I should just draw this. In the second quadrant, we end up at pi. Pi is approximately 3.14. And remember, pi over 2 was approximately 1.6. So in quadrant 2, we have values between 1.6 and 3.14. So clearly, our arc length is in quadrant 2. In quadrant 2, sine is going to be positive, but cosine is negative. Okay, what about an arc length of -1? So this time what we want to do is we want to go in the opposite direction. Remember, we're starting off at 0. And if we go in the negative direction, we're at negative pi over 2, which is going to be approximately negative 1.6. So a value of -1 is actually in this quadrant, which is quadrant 4. And in quadrant 4, sine is negative, but cosine is positive. Let's continue on with using all of these properties that we've discussed so far. This time we're going to use a calculator. Make sure that when you use your calculator that you are in radian mode. We're not really looking at degrees at all at this point. We are in radians. We want to approximate the value for cosine and sine for each given arc length S. And then we want to state the quadrant in which the point corresponding to S lies. And we want to find an approximation for tangent, cotangent, secant, and cosecant. So let's say we're looking at an arc length of 0.95. All we would have to do is, in your calculator, use the cosine function, put in 0.95. make sure you're in radians. And I think I'm going to go out to, let's see, 0. I get a long decimal. Maybe I'll do 58168. If I put in sine of 0.95 into my calculator, I get 0.81342. So that would be the part A. I found an approximation for cosine and sine. Now in part B, I want to know what quadrant I'm in. Well, 0.95 is between 0 and 1.6, so I'm in quadrant 1. So it makes sense that when I put in 0.95 into my calculator, sine and cosine are both positive. And also notice that the values are between -1 and 1. So remember, the values for cosine and sine are always going to be between -1 and 1. So if you got a value that was larger than 1 or smaller than -1, like a -2 point something, that would tell you that you're probably in degrees, and double check. Make sure you're in radians. So depending on what calculator you're using, you may not have a cotangent, secant, cosecant key. You should have a tangent. So if we were going to put tangent of 0.95 into our calculator, I get approximately 1.398, 38, and I'll stop there. So notice that this is greater than 1, and that's okay. The other four trig functions can be larger than 1 or smaller than -1. It's only sine and cosine that are restricted to having a range between -1 and 1. How would we find cotangent? Well, what you could do is, in most calculators, they have a 1/x key. You could find tangent and then hit that 1/x key in your calculator, and that tells you you're going to find the reciprocal value. So that would give you, if you were putting this in a calculator, 0.71511. Maybe I shouldn't have put that there. Let's see, what did I get? 0.71511. And then secant, you would do the same thing for secant. Remember, secant is the reciprocal of cosine. So find cosine of 0.95 and use that 1/x feature in your calculator, and you should get 1.71915, and I'll stop there. And let's see, I'm going to squish cosecant in here. Cosecant is a reciprocal of cosine, or sine, sorry. So put in sine of 0.95 and do the 1/x, and you should get 1.22938. Double check me, because I might have accidentally gotten out of radians and went back into degrees in my calculator because it turned off during this video. Let's see, number 2, our arc length is -1.8. So again, just putting these values in a calculator, we get cosine of -1.8. That's going to be approximately equal to -0.22720. And then sine is going to be negative. Oh, they're both negative. -0.97385. So now when I look at -1.8 and I look at the unit circle, I go clockwise. 0 to negative 1.6 is quadrant 4. If I go a little further to negative 1.8, I'm in quadrant 3. So my sine and cosine should be negative, but I didn't have to do that. If I put these values in my calculator and I get that cosine is negative and sine is negative, they're both negative in quadrant 3. Whoops, B, sorry. So I'm in quadrant 3 that I can find either by looking on the unit circle for an arc length of negative 1.8 or just noticing that both sine and cosine are negative, so I must be in quadrant 3. Okay, so if we're going to look at values for tangent, let's see, in my calculator, I get 4.28626. We'll go to cotangent of negative 1.8. Use your 1 over x key if you have it. It just depends on what calculator you're using. I have 0.2, double check me on this, 2, 3, 3, 3. How many threes I got? 2, oops, 2, 3, 3, 3, 0. I'll stop there. So secant of negative 1.8. Secant is a reciprocal of cosine. I have negative 4.4013. I'll stop at 7. And then cosecant of negative 1.8, that would be the reciprocal of sine, which would be negative 1.02685. I'll stop there. Okay, so let me think. I'm in quadrant 3. In quadrant 3, tangent, cotangent are the only positive trig functions, and when I plugged it in a calculator, I got that they're positive. All the others should be negative, and yes, they are all negative. So that tells me I'm probably correct. So let's look at some exact functions that we can get. We were just looking at using our calculator or looking at our known values for 0, pi over 2, pi, 3 pi over 2, 2 pi, and so on. But what if we want to find some exact values, not using our calculators, for some other common values that we use for arc length? So one of those values that we typically use is pi over 4. If we look at pi over 4 on our circle, it's going to be the halfway distance in the first quadrant. If I go ahead and drop myself a right triangle, and it may not look like it is because my drawing's a little sketchy, my x value and my y value, they're going to be equal to each other. Because this is the halfway point in quadrant 1, so the x and the y values are going to be the same. So I do have that x is equal to y at this particular point. So remember the unit circle, the equation is x squared plus y squared is equal to 1. So now I can just replace either the y or the x with, so I could replace x with y, and then I'd get y squared plus y squared is equal to 1, or I can replace the y with the x, which is what I'm going to do. Oops. Talking and writing. X squared plus x squared is equal to 1. So what I'm trying to do is just get an equation with one variable so I can solve this. Now I have 2x squared is equal to 1, or x squared is equal to 1/2. Square rooting both sides. Remember, we have this plus minus whenever we square root. So x is going to be plus or minus the square root of 1/2. Now I'm in quadrant 1, so I know in quadrant 1 my x value is going to be positive. So from there I can conclude that x is equal to a positive square root of 1/2. which is the same as 1 over the square root of 2. I didn't want to write the 1/2 under that whole square root. So that's going to be the x value at that point where the arc length is pi over 4. However, we need to rationalize. So I get an x value of square root 2 over 2. And since the x and the y are going to be equal, y is also square root 2 over 2, which tells me when I have an arc length of pi over 4, it's going to be corresponding to the point square root 2 over 2, square root 2 over 2. So we found one point, so we have exact values for our x and our y, and there are other common values that we use as well. Pi over 4 corresponds to an angle of 45 degrees if I was going to change it. Going back to this circle, there are some other common angles that we use. If we looked at, say, pi over 6, that's a common value that we use as well. We would do the same thing. We would drop ourselves a right triangle. In this case, this one is a little bit more difficult to solve since the x and the y values are going to be different. We have to get a little bit more creative when we solve, but we will find that at pi over 6, we're going to have an x value of square root 3 over 2 and a y value of 1/2. And this would be a 30-60 triangle from geometry. If we were to look at this value of pi over 3 and drop ourselves a right triangle there, we would get an x value of 1/2 and a y value of square root 3 over 2 once we did our little distances and proof. It's actually a pretty long proof if the x and the y values are not the same, but you can look in your textbook and find the solution to the pi over 6. However, you don't have to do that because there is a table that is provided, and that gives you the exact function values for pi over 6, pi over 4, and pi over 3. So recall we already had 0 and pi over 2. So in the first quadrant, we already know the value for 0, but let's look at pi over 6. So if we have an arc length of pi over 6, the value for sine is going to be 1/2. The value for cosine is going to be square root 3 over 2. The value for tangent, square root 3 over 3, and then we could look at the other values as well. This brings us to all the common values that we'll see on the unit circle. Notice that we have already figured out our first quadrant. Given these values, arc length of 0, pi over 6, pi over 4, pi over 3, and pi over 2, we now have the corresponding points. At 0, we have 1, 0. At pi over 6, our x value is square root 3 over 2, our y value is 1/2. At pi over 4, x and y are the same. They're both square root 2 over 2. Pi over 3, the x value is 1/2, y value is square root 3 over 2. And then we get to 0, 1. So what I wanted to point out is all you really have to know is first quadrant. Once you have the first quadrant, you have all the quadrants. Because notice that the values are all the same in quadrants 1, 2, 3, and 4 for those points. The only difference is sometimes you'll have a negative instead of a positive, depending on what quadrant you're in. So in quadrant 1, oh, I don't want that. Why do I always do that? Now in quadrant 1, x and y are both positive, so look at the points. 1, 0, square root 3 over 2, comma, 1/2, and so on. All the x and the y values are positive. Now, if we continue on into quadrant 2, in quadrant 2, our x values are negative and our y values are positive. This is what I wanted to point out. Let's just say we're at the point in quadrant 1 that corresponds to pi over 3. I'm at the point positive 1/2, positive square root 3 over 2. If I go straight across to the point that corresponds to 2 pi over 3, so still over 3, the values are the same. You still have 1/2 square root 3 over 2. The only difference is now the x value is negative because we're in quadrant 2. But the y values are still positive. What if I were to go to quadrant 3? If you go from 2 pi over 3 and you go straight down to quadrant 3, you're at the point 4 pi over 3. So pi over 3, 2 pi over 3, 4 pi over 3, same denominator. Also notice the point, still 1/2 square root 3 over 2. But this time, since we're in quadrant 3, x and y are both negative. But those values are still the same, it's just that they both happen to be negative. Let's continue on from 4 pi over 3, let's go to 5 pi over 3. Again, look at the point. Still half, still square root 3 over 2, but now the y value is negative. And then if we continue on, we're back up to quadrant 1, where half square root 3 over 2, both positive. And you can do that for all the points on the unit circle. In quadrant 1, pi over 4 corresponds to square root 2 over 2, square root 2 over 2. If you go across to quadrant 2, it corresponds to 3 pi over 4. Same values, except for you got a negative and a positive. Continue on. We're at 5 pi over 4. Same values, both negative. 7 pi over 4, same values, x positive, y negative, and then we're back. So again, this is that nice symmetry of our circle. So as long as you know quadrant 1, you have all the values for all the other quadrants. You just have to determine if x is negative or positive, y is negative or positive. Now there's a cute little trick on how you can remember the values in quadrant 1. And then just use all students take calculus to remember which ones are negative and positive for the other. And that would be this chart here. So notice on the unit circle, if we look at quadrant 1, cosine at 0 starts at 1, and then it gets smaller and smaller and smaller as you go around until at pi over 2 cosine is 0. So in quadrant 1, cosine starts at 1 and it ends at 0. Another way to write the value 1 is to write square root of 4 over 2. So why would I even do that? And that's because there's a pattern. Notice at pi over 6, cosine is square root 3 over 2. Pi over 4, it's square root 2 over 2. At pi over 3, cosine is 1/2, but another way to write 1/2 is square root 1 over 2. At pi over 2, cosine is 0. Another way to write 0 is square root of 0 over 2. So really it goes square root 4, square root 3, square root 2, square root 1, square root 0. And once you have cosine, you have sine, because sine does the opposite. Sine starts at 0 and it ends up as 1. So sine increases, cosine decreases. So if you're looking at sine, it goes from 0 to 1. Which is square root 0, square root 1 over 2, square root 2 over 2, square root 3 over 2, square root 4 over 2. So just little tricks to memorize. The first question on exam 1 would be for you to fill in this unit circle with the values of the radians along with the points that they correspond to. So we'll use that circle and we'll find exact values, but here we do not want to use a calculator. So what about sine of 5 pi over 3? Well, you would look at your circle and see if you can find 5 pi over 3. And I see, now I've written all over this, but I can see that I have 5 pi over 3 in quadrant 4. So I'm in quadrant 4. 5 pi over 3 corresponds to the point 1/2 negative square root 3 over 2. And since sine is the y value, it would be the negative square root 3 over 2. Okay, and that's how you would use this unit circle. You just have to remember that those arc lengths are reduced. So you wouldn't want to write something like 6 pi over 4. You would write 3 pi over 2. Reduce all your fractions. So sine of 5 pi over 3 is the same as, is equal to, negative square root 3 over 2. What about cosine of 23 pi over 6? Well, 23 over 6, that fraction is reduced. So one thing I could do is, and this is a nice thing about this circle, is there's this idea of symmetry, of this idea of counting. So I could count by pi over 6s. So let me show you what I mean. I wonder if I can, yeah, I can erase all this. So let me go back to this unit circle and we'll look at counting by pi over 6. Let's say that I'm at pi over 6. So I've gone this pi over 6 distance. If I go another pi over 6 distance, I'm at pi over 3. So what I've done is I've started at 0 pi over 6. I've gone 1 pi over 6. And then I've gone 2 pi over 6, which reduces to pi over 3. If I go another distance of pi over 6, I'm at 3 pi over 6, that reduces to pi over 2. So I can count by pi over 6s. That would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. At 23, I'm at 11 pi over 6. So that was tedious, but doable if you have a unit circle in front of you. That tells me the cosine of 23 pi over 6 is the same as cosine of 11 pi over 6. So the other way that we could get around counting that much is to just look at 23 pi over 6, subtract 2 pi, which would be what, 12 pi over 6? And we would get to 11 pi over 6. So using that idea of coterminal from 9.1, and that may be the shorter one to do, but you can also count because everything is really uniform on the unit circle. So you can count by pi over 6s, by pi over 2s, by pi over 4. You can even count by pi over 3s, although that's a little bit more difficult to see. Cosine of 11 pi over 6, going back to 11 pi over 6. Cosine is the x value, so that would be positive square root 3 over 2. Let's look at C. We have tangent of 7 pi over 6. Go to our unit circle. See if we can find a 7 pi over 6. And I see in quadrant 3, I have 7 pi over 6. Tangent is the y over the x value. So the y value here is going to be 1/2. The x value is square root 3 over 2. I can just go back to that chart that we had earlier, but maybe the chart was only in quadrant 1. But you could still do that. We can go back to the chart we had earlier and figure out what value 7 pi over 6 corresponds to, and 7 pi over 6 corresponds to pi over 6 in quadrant 1, and then tangent in quadrant 3, so 7 pi over 6, would give us the same value as tangent in quadrant 1 for pi over 6, and it's positive. So you could do that. You could simply look at the y and the x value on the unit circle and say that this is equal to negative half over negative square root 3 over 2. Notice that the negatives will cancel, and that makes sense because tangent in quadrant 3 is positive. So what we'll get is, after you do the math, you'll get positive 1 over the square root of 3. And then you would rationalize by square root 3 over 3, which would give you the square root 3 over 3. Let's try another one. Secant of 5 pi over 6. So secant is the reciprocal of cosine. Another way to look at secant is that it's the value of 1 over x. So we'll go to the circle. If you go to 5 pi over 6, so again, remember this is going to be a 1 over x. If you look on your unit circle at 5 pi over 6, you'll see that that's going to be a value of negative square root 3 over 2 for the x value. So we're going to be in quadrant 2 where cosine is negative, and at 5 pi over 6 cosine is negative square root 3 over 2. So this is going to be the reciprocal, so it's 1 over negative square root 3 over 2. And then that becomes negative 2 square root of 3. Have to rationalize. Negative 2 square root of 3 over 3. Part E, we have cotangent of negative 3 pi over 4. So if you go to positive 3 pi over 4 on the unit circle, maybe I'll just draw one. Positive 3 pi over 4 is going to be in quadrant 2, and it's at halfway point in quadrant 2. So whenever you want to find a negative, what you're going to do is you're going to reflect about the x-axis. So negative 3 pi over 4, that's actually going to be in quadrant 3. And cotangent is the x value over the y value. In quadrant 3, this is going to correspond to 5 pi over 4. So negative 3 pi over 4 and positive 5 pi over 4 are going to give you the same values. It's going to be a negative square root 2 over 2, negative square root 2 over 2. That's the point that it's passing through. Cotangent is simply going to be equal to negative square root 2 over 2 over, so that would be the x value, over the y value, and then you'll get 1. Last example would be cosecant. Cosecant is the reciprocal of sine. It would be a 1 over y value. And at negative 7 pi over 4, well, what we could do is look at positive 7 pi over 4. Positive 7 pi over 4 is in quadrant 4, and it's at halfway point. If we flip along the x-axis, we'll be in quadrant 1. So that would be negative 7 pi over 4, and it actually corresponds to positive pi over 4. The other thing you could do when you have these negative values is, remember, you can count. You can just go in your unit circle and count how many pi over 4s until you reach negative 7 of these pi over 4s. So since we're at positive pi over 4, the x and y values square root 2 over 2, square root 2 over 2 are going to be positive. So our cosecant is going to be 1 over the positive square root 2 over 2, which would be 2 over the square root of 2. And then I would have to rationalize. by multiplying by square root 2 over 2, top and bottom. And we get 2 times the square root of 2 over 2, which reduces to just the square root of 2. This is a very long section. So for these last examples, what we're going to do is we're going to use the idea of those reciprocal identities and the Pythagorean identities. So that was on our page 2 at the bottom. And in example 6, we're going to find tangent, cotangent, secant, and cosecant for given the values in part A and part B. So we're going to use what we're given to find the rest without using a calculator. In part A, we have that sine of S is 3 over 4, and cosine of S is negative square root 7 over 4. So if I wanted to find tangent, remember tangent is sine over cosine. But I don't think I want to do tangent first. Since I already have sine and cosine, maybe I'll look at the reciprocals. So the reciprocal of sine is cosecant. So cosecant of S, remember I don't have the arc length S, but I do know that its sine of that is going to be 4 over 5. So since cosecant is the reciprocal of sine, it's simply going to be equal to not 5 over 4, sorry, 3 over 4, 4 over 3. So I have cosecant. And since I have cosine, I get its reciprocal, which would be secant. So I have secant of S is equal to negative 4 over the square root of 7. However, now I have to rationalize. So I get secant of S is going to be equal to negative 4 square root of 7 over 7. Maybe I will box these since I'll probably be making a mess here. So I found cosecant and I found secant. Now let's work on tangent. So tangent of S is going to be equal to sine over cosine. Whenever you have a complex fraction where you have a fraction in the numerator and denominator and they have, say, the same denominator, notice that these both have the denominator of 4, it's actually going to cancel. So now you can rewrite this as 3/4 times the reciprocal. So that would be times negative 4 over the square root of 7. You could cancel the 4. Or you could notice that since these denominators are the same, they're just going to cancel. And this becomes negative 3 over the square root of 7. So tangent of S is equal to negative 3 over the square root of 7. However, we still have to rationalize. So I'm going to multiply by square root of 7 over square root of 7. And then let me rewrite this as tangent of S equal to negative 3 square root of 7 over 7. Now that I have tangent, I easily get its reciprocal, which would be cotangent. And instead of looking at negative 3 square root of 7 over 7, I'm going to go back to the negative 3 over the square root of 7 because I noticed that if I take its reciprocal, if I flip it, then I don't have to rationalize. It would be equal to negative square root of 7 over 3, and I'm done. So I found all 4 values. Our last example in this section is going to be given the value that sine of S is equal to 4/5, and we know that S is going to be in quadrant 2, but that's all we have. We don't have cosine or any of those values. So let's go ahead and find the other values. Well, since I have sine, I know that I'm going to have its reciprocal, which is going to be cosecant. I get that right away. I have cosecant of s is going to be the reciprocal 5 over 4. And now notice that I have cosecant of s. You always have to have an argument in there. Sometimes people get lazy and they just write cosecant equal to 5 over 4 and they forget the s. That doesn't make sense. That's like saying f of x equal to 5 over 4, instead writing f equal to 5 over 4. It makes no sense. You have to have the argument s in there. However, I have sine, I have cosecant, I have a problem because I can't get any of the other functions. So what I'm going to go back to is I'm going to go back to the Pythagorean identities. Notice that I have that cosine squared plus sine squared is equal to 1. And I have sine, so I can actually find cosine, even though that's not part of the question. I can still find cosine by using the Pythagorean identity. And once I have cosine, then I can find its reciprocal, which is secant. So let me use, and I'm going to write it as, let's see, cosine squared s plus sine squared s equal to 1. So cosine squared s plus sine is 4 over 5, and I'm squaring it. That has to be equal to 1. That would be 16 over 25. So cosine squared of s is going to be 1 minus 16 over 25. And I'm going to skip some algebra. So 1 is going to be 25 over 25. 25 minus 16 is 9. I get cosine squared s is equal to 9 over 25. And now if I square root both sides, I get cosine of s is equal to plus or minus the square root of 9 over 25. And then the square root of 9 over 25 is 3/5. So that's equal to plus or minus 3 over 5. I don't know which one to choose. However, going back to part B, it says that S is in quadrant 2. So since I'm in quadrant 2, I know that cosine is negative. Now I have cosine of S is equal to the negative 3 over 5. Although that wasn't asked for in the problem. Now that I have cosine, I can find its reciprocal, which would be secant. So secant of s is going to be negative 5 over 3. This is a nice problem because I haven't had to rationalize anything yet. Okay, so I have cosecant, I have secant. I still need tangent and cotangent. So tangent is sine over cosine, and I have sine and I have cosine, so I can get tangent, oops, I want blue. Tangent of s is going to be equal to sine, which is 4/5, over cosine, which is negative 3/5. Now remember that shortcut, same denominator, cancel, cancel. Tangent of s is equal to negative 4/3. It makes sense that it's negative because we're in quadrant 2 and tangent is negative in quadrant 2. Okay, last thing I have to find is cotangent, piece of cake because I have tangent. Cotangent is the reciprocal. Cotangent of s is going to be negative 3/4. And that's the end of this section. Again, super long. Sorry about that. Covered a lot of topics. So that's it.